So, if you guys, today's class will be short, so no worries. I always wanted to discuss this with you. So, what is multi-stability? So, many of you already know about chaos, or already know about 1D maps. So, nonlinear dynamics. We have reached almost the end of this course. So, what we have learned so far? We have learned about 1D maps, then 1D flows, then we came again to 2D. Yes. So there is another rich class, that is three-dimensional maps and 3D. So as many of you today presented about Lorentz attractor, those are three. So those are represented by three-dimensional differential equations. And keep in mind that in Van der Waals oscillator, it's a two-dimensional system. You did not observe chaos. Those who have presented Van der Waals oscillator, did you observe chaos? Yes. So 2D flows don't show chaos. 1D flows don't show chaos. Okay. But the minimum dimension for chaos in a flow, that is an ordinary differential equation system, is 3. So minimum dimension for a flow to show chaos is 3. Whereas for maps, the minimum dimension is just 1. Just logistic map, you can see chaos. Okay. So therefore, in order to understand chaotic orbits, chaotic dynamics, you always start with the least dimension, that is 1D maps. These are the first examples we show to understand the chaotic dynamics. Okay. So therefore, now you can relate why I started teaching 1D maps first and not Rossler attractor or Lorentz attractor at the first. So hope you are getting the rewind of what is happening. Okay, so what is the topic we are going to discuss today? It is about multi-stability. Okay, come to know, but I want to actually motivate you. What is multi-stability before we begin it? So just I will ask you one simple. That is, if you know about this equation z cube minus 1 equals to 0. Of course, this is a complex equation. It has complex roots. So what are the roots? 1. No, 1 omega omega square. Okay, check it again. 1 omega omega square. So these are known as the cube. So what happens? Why they are known as the cube roots of unity? So in a unit circle, it's of unit radius. 1 here, omega and omega square here. It will lie on the circle like this. All right. So now this equation has 3 roots. This equation has 3 roots, and if you remember in my numerical methods class in the previous semester, I showed the basin of attraction diagram. So it was giving a fractal structure. Do you agree to it? No? How many of you don't remember that? So what I ask you now is, suppose you started from, you want to solve this, you started from 0.5 to solve this equation by Newton-Raphson method. Newton-Raphson. And Newton-Raphson method needs a starting initial guess, isn't it? So you started from 0.5. Applying the Newton-Raphson method as a hope that it will converge to either the root 1 or 3. Yes. Now, can you tell me which one? How? Suppose you take 0.8, suppose you take 0.9, which will it converge to? Why are you saying 1? Why are you so sure? So I want to show you something about Newton fractals. So you can see it here. You can see that the fractal image will be something like this. Okay, so you can see this here. This is shown for the f of z minus 1, the same polynomial I have taken it here. Okay, what we are doing here, we are taking 3 different colors. We are taking 3 different, starting any initial point here. If you take any point here on this domain, it will converge to the root marked by red. If you take any point here, it will converge to the root marked by green. Any point initial condition here, it will converge to the marked with blue. Okay, but the interesting thing happens near the boundaries. Okay, you can see that near the boundaries, it is behaving very complex. So what happens if you take root in here? So a tiny change in the decimal point will shift. That means a tiny change in initial condition by a decimal point by a factor of even 0.01 or 0.001 will change the root convergence. It can converge to, if you take 1.4, it converges to red. Suppose this one red, and suddenly by a plus 0.001, 1.4001, then it converges to blue. So you can see it. So how complex it is. Okay. So why I showed you this diagram? It is the best example of multistability. So that equation z cube minus 1 exhibits three roots at the same instant, but at a particular initial condition will converge to only at a time. You choose one initial condition. Will it converge to three roots at once? No, it will converge to one root. Okay. So it is getting settled at one root. If you take another initial condition, it is getting settled at another root. Another initial condition, it gets settled to another. Like that, if you make a heat map, you get this structure. Basin of attraction. Okay, this is known as a basin of attraction because you see throughout this grid, so this is a grid actually. Throughout this grid, you see which point converges to which root. Okay, and you mark that with a color. That's how you generate this basin of attraction diagram. Got that? So what I meant to say is the basin of attraction diagrams are usually fractals. That's what you see here. Okay. Okay. So this is what I am trying to motivate you about multistability. Okay. So hope it is clear. Is it clear? So now another example is of a coastline, like say, suppose this one, this is a valley. This is a valley. Okay. What you do? You take a ball, take a ball here, okay, and drop it. Drop it. What will happen? Which side it will go? How many of you are saying left? Raise your hand. How many of you are saying right? Raise your hand. How many of you are saying left? Left. How many of you are saying left? Okay, Mohammed Harun is saying left. Okay. How many of you are saying right? So yeah, so now you can see that there are two different perceptions. There are two different perceptions of multistability. So it depends. It depends. A tiny, maybe here if you push, it will go definitely here. It might go this side. So a tiny change in initial condition can shift your attractor. This is are the attractor because these are the steady state. Why these are the steady state? Because if you push the ball here, it can fall down. It can fall down and be here. So you can see just by changing a bit of initial condition, it change the attractor to where it goes. Okay, technically it has more than one attractor, isn't it? Does it have only one attractor? It has more than one attractor. But the initial condition you choose depends which attractor it will go. So that's what exactly multistability is. Multistability means it has more than one attractor where it converges to, depending on the initial condition. And multistability is very much popular among students. Okay, why? Because some might be looking to me, but they might be thinking of something else. So their visual perception is to me, but their mind perception is at somewhere else. Okay, so they might be in many other dimensions. Okay, they might be thinking tonight is Friday, so we should have biryani night, and maybe we'll watch this movie. Maybe we'll go here, there. But at the same time, you are focusing. So you are doing many multiple things at the same time in your mind, believe or not. So your human body is a very good example of multistability. Like whether you say it or not, your heart beats. Whether you say it or not, your blood flows. Whether you say it or not, your like you get signals to your mind, your neuron fires, everything happens at the same time. Okay. So let us now come to the theoretical definition of multistability. So multistability means it defines the coexistence of several possible final stable states, or mainly you can say it attractors. It can be a chaotic attractor also. Here, why we are saying chaotic attractor? Because when you start from an initial condition and iterate your map, then you can see chaotic trajectory. Okay, fine. So this is multistability. The final state to which the system will converge, it depends crucially on the initial conditions. I hope you can deduce what is meant by this from the diagram I showed you for the Newton fractal. A tiny change in the initial condition can lead to the long-term dynamics can lead to two different outputs. Okay, that's what multistability is all about. So the set of initial conditions that give rise to a set of trajectory converging towards the same attractor called basin of attraction. What is a basin of attraction? That is computationally intensive to plot. Basin of attraction is computationally intensive, actually. If you want to have a very fine resolution, it can take some days also. So that's where parallel computing comes. And like parallel computing or using cores, different cores, cluster use can come. And usually the basin of attraction, if you see, it is rather complicated and it exhibits a fractal structure. So yeah, so therefore there exists a non-trivial relationship between the coexisting attractors or asymptotic states and their basins of attraction. You cannot predict a basin of attraction. As I will show you now, you remember the Newton's fractal, how it was looking as the Newton fractals. Okay. Now I will show you a version done in my PhD thesis. My PhD thesis was mostly on multistability, and I will show you that it is possible to have infinitely many attractors at the same time. Z cube minus 1, you saw 3 attractors, 3 roots. Now I am trying to show you that I can design a map which can exhibit a 2-dimensional map which can exhibit infinitely many periodic points, infinitely many attractors. Okay? And we will see the basic. So yeah, the region of coexistence of many stable states is a critical. A small noise or any other external perturbation may switch the system from one attractor to another. I hope that is also clear to you. Just think about the Z cube minus 1 fractal structure. I told you, just a tiny perturbation of decimal point can shift your attractor from red to blue. Yes. Yeah, you can see Z5 minus 1. You can try. You can try to find. Yeah, but that is not related to this map. There is a confusion. Like you can try this maybe next class. I want to see like Z5 minus 1 you can try, Z20 minus 1 you can try, Z100 minus 1 equal to 0 you can try the fractal structure. Got it. I want the whole class to try this experiment. I want the whole class to try this experiment. So Z cube minus 1 equal to 0. Draw the fractal. Okay. Then increase Z to the power n minus 1. Take different values of n and draw the fractals. N equals to 3, n equals to 4, 5, 6, maybe till 100. Okay. Can you do that? So this code you can easily get on web. The fractal structure, you can say Newton fractals. Fractal, search on Google, you can get a Python code. Just try the code for n equals Z to the power n minus 1 equal to 0, fractal structure, n equals to 100. But mind you, the more number of roots you have, the more colors you need. But you have only 7 colors. Okay. So you need to have some variation of colors. But I leave this assignment to you next Friday. Okay. So everyone should do this computational assignment. I want to see. Okay. So you show me how the fractals look like in each of the cases. Everyone got the idea? This is the computational assignment. The phenomenon of multistability has been found in almost all areas of science and even in nature. Okay, so we will see something related to the visual perception right now. Okay, let us see. Try to see this image. Try to see this image over here. Maybe I will leave this case to you to understand, but I will start from this case because it is easier. See this example. See this image on D. What you see? You might be seeing a vase, some apples or oranges. Okay. Yes. But at the same time, you can see there are two faces looking into each other. Is it clear enough? Huh? Yes. So illusion is one of the topics. Illusion. Why illusion occurs is multistability. Because there are multiple states your eyes is trying to reach to. Okay, and that is a very great example of multistability in visual perception. Okay, so you can see that here your eyes, maybe Nikhil's eyes first thought it is a vase because I told so. Because I told the vase, so you thought it is a vase. You thought like that and you saw that. Then when I said that yes, there are two persons looking into each other, then your mind went into that direction and you actually saw that yes, it is a two persons looking into each other. So you can see how your eyes are, how your brain are thinking into two different ways. So this is where your eyes are getting attracted to, and hence it is known as an attractor. Okay, there are two possible states, hence it is an attractor. Similarly, I would suggest try to see this and think. Okay. So you can see all these images A, B, C, D, E, F, all something in common. I urge you to see each of them and think what it is. For now, let us go to G. Okay, let us go to G. Yeah. These are special names. These are discovered by scientists already. So these are examples of ambiguous figures leading to bistable perception. Okay. So you can see that the first image on the A is known as the Necker cube. So this is known as the Necker's cube. The part B is known as the Kafka cube. Part B is known as the Kafka cube. C is a stair, that is a Schroeder stair. D is Rubin's face and vase. Okay, and yeah, I did not capture the others, but this is a famous picture. This is a famous picture. So I don't remember the scientist name. Escher, yes, Escher. So you can search for Escher, and he was a scientist drawing who liked to draw these kind of images. Okay, you can see that in this image, you cannot, if you start climbing here, you might feel falling down. Okay, but then this is the leading to the house inside. Okay, so this is the picture where you will get, you might feel that I have to go there, and while climbing, you will again fall down. Okay, so this is a very nice painting. Similarly, you can see this one. Okay. Fine. So if someone is interested, I would like them to read this early cross-modal interactions and adult cortical plasticity revealed by binocular rivalry, mainly who are from understand more. Okay. Yes. So yeah. So yes. So what is an attractor basically? An attractor, roughly speaking, is a subset of the state space to which orbits originating from different initial condition tend to tend to that state as time increases over a long period of time. Like after a long evolution of time, you start from an initial condition, run your system again and again repeatedly over a long period of time, and watch where it converges to, and that is known as an attractor. Okay. So it is common for dynamical systems to have more than one attractor. More than one attractor. So for each such attractor, its basin of attraction is the set of initial conditions leading to that attractor. Okay. So yeah, you what you want to understand is which initial condition leads to which attractor. Which initial conditions leads to which attractor. Okay. That's the idea of basin of attraction. Fine. So. Yeah. So we'll see some websites before we diverge. Hmm. So yeah, these are some good examples I would like to show you from the Duke group. I think Duke University. So you can see that this is a good example of a mechanical system. This is a good example of a mechanical system known as snap through buckling. Okay, what is buckling? Buckling means what is buckling? Yes. So imagine yourself holding uh, holding your friend. Okay. Then one other friend came on top. You're holding still. One other friend came on top. You're still holding. Then you are buckling. Okay. You will feel like, yeah, it is too much for me. You are buckling. Then there will be a limit where you fall down. Okay. That's what happens. That is known as buckling. And same thing happens in your mechanical systems. Okay. So thin structures such as aircraft panels are susceptible to loss of stability or buckling before strength of limits are reached. Okay. So you can see the snap through buckling, this phenomena in aircraft. Okay, imagine you must be in aircraft. Okay, then you feel that it's done. Okay, so such kind of things occur because there are multiple stable equilibrium coexisting. Okay, there are different kinds of sound, but since it is some noisy things, it is making some abrupt sounds. So this creates the potential for large oscillations about and between the equilibrium. Okay. So you can see that they have done a lot of study here. So yeah, roller coaster oscillator, and they have done some experimental studies also in nonlinear dynamics. So I would leave it to you to explore. There's yeah, this is one of the basin of attraction diagrams. You have four coexisting attractors here. Four coexisting attractors. Therefore, in the basin of attraction, you kind of see four different colors: yellow, orange, red, black. Different colors, and you can see how complicated this diagram is. This is a fractal looking structure, but it's highly complicated. But this kind of phenomena, I ask you, go to your home, take fridge out of the milk, take milk out of the fridge. Sorry, take out of the fridge, okay, and then put on a small cup. Put on a small cup, okay. Then put colors. Put some colors. Those who have colors, especially girls, those who have colors, you put colors, okay, like different color droplets, red, green, blue, and then mix it up. Then mix it up, okay. Don't mix TV top or any which is vibrating. Let them mix naturally, okay. Then you will see this kind of image, fractal. Okay, try to do this and let me know next class. Take photos and share it with me. Okay, everyone may be with different shapes. Maybe one can use the circular dish. Maybe one can use the triangular dish. One can use square dish. Okay, maybe show me. Send me the examples. I will show it in the next class. I will discuss it. Okay, got that? This is home exam. Home assignment. Huh? Hostel, yeah. Wherever you can get milk from, get milk and do that experiment. So you can see even this nice fractal looking structures over here. So this basin of attraction can vary a lot, and you can see these structures, and obviously they have some kind of symmetry. Okay, depends on your system. If your system is symmetrical, that means your location of periodic orbits or location of attractors will be symmetrical. If the location of attractor is symmetrical, then the basin of attraction will also be symmetrical. Kind of symmetrical. Like, yeah, initial condition here will converge here, initial condition here will converge here. Like that, they will make the symmetrical structure. So, yeah, you can see these lot of things here. However, I will leave to you to understand all of the structures. I mean to say that this coexistence of attractor or multistability is a huge problem in mechanical. Always try to reduce the multistability and reach to a not multiple states. Okay. Imagine your mind is also, if it is multi-stable, you don't like it, isn't it? Because suppose you are preparing for exam. Tomorrow is your exam. Suppose tomorrow is your nonlinear dynamics exam. But today is India versus South Africa T20 World Cup. What you will do? You want to watch it. You also want to watch. You also want to watch my videos. Very rare. Okay. Or you also want to see my lectures or read nonlinear dynamics. So your mind is very confused what to do. So this is multi-step. So you can see these have been seen in damping like this impact and friction systems. Impact friction see in real life. Okay? Anyway, so these are all experimentally observed. These are mind you, these are experimentally observed. These are not numerically seen in Python or anything. They have experimentally observed these things. Okay, so you can see experimental is this and numerical data is this. Almost similar, but still complicated looking. Okay, so I meant to say that it is just not what I say um, theoretical, but rather it is computational. Okay. Yeah, just one example before we leave. So, yes. So you can see this, how the basin changes as you vary the parameters over here. So three roots, and you can see how this attractor is changing, the basin of attraction is changing. Okay. So that's one of the images. So this is just one example. And before we stop, I just wanted to show this, the case of infinitely many attractors. But I cannot show infinitely many attractors, so I have just shown 15 of them. So I have just shown 15 of them. This is the picture from my PhD thesis. Okay. So you can see that these are the 15 different periodic orbits. Okay. So this is a period 1 orbit. So this is a period 1 orbit. This is a period 2 orbit. Like it goes here, then here, then here. Okay. This is a period 3 orbit. 3 orbit like that. You have 15, period 15 orbit. And I have given different colors to different periodic orbits. Maybe when you are doing this assignment, you can use this idea. Okay. So I want to see how the basin of attraction looks like. Okay. So you can see that here in the red, if you take converts to the fixed point. If you take any initial condition on the blue region, it will converge to a period 2 point. Okay. So like that, you can have multi-stability, and I have shown the zoomed part of this image here. The zoomed versions are shown here. Okay, you can see how regularly they are distributed. Okay. Yeah. How regularly they are distributed, but yeah, they are quite interesting. I would like to say to you. So this is what, yeah, this is what. If you are here, it is quite easier to get attracted to. But if you are here in this region, if you are in this region, then it is very complicated. If you are in these regions, the boundaries, the fractal boundaries are very rough. Okay, you cannot predict where the point will go. So you can see that it is looking like shrimps, like prawns. Okay, prawns. So shrimp, we call it as shrimps. Okay, so this is one such shrimp you see here. So same in different other cases also. So this is what multi-stability is all about. These are all known as the basins of attraction. You understood the basins of attraction? Hmm? Okay, so this is just a small talk on multi-stability I just gave to you. Okay, so just a basic idea. So next class we can just see something else, and maybe next class you have exam, and also this computational assignment, and also you need to send me the photos of the milk with different colors. Okay. Sorry.